introduce Jan Tuitman, who is going to tell us about counting points with a deformation method.
This is all joint work with Sebastian Braunkrantz, who did his PhD here in Oxford up until last year. So I wasn't quite sure. There's some real experts in the room, other people who've probably never thought about point counting. So I've tried to strike a balance and start with a very general introduction and then move on to more technical stuff. So let F be a finite field, Fq be a finite field with Q is p to the a elements. Slightly non-standard to call this A maybe, but I need n for something else later on. And X is smooth hypersurface of degree d in Pn. So in particular, X has dimension n minus 1. Yeah, so then we can define the zeta function like this. That's all clear for everyone, I guess. It contains a number of points of X over all the extensions of Fq. It turns out to be a rational function by the wave conjectures. And the problem is to compute it efficiently. Well, that's very clear. I think it's already been mentioned before this week. So, like other p-adic algorithms, I use p-adic cohomology to do this. So I don't really want to get into the construction because that would take up the rest of my talk, maybe 3 or 4 talks. So there is a way to define these rigid cohomology spaces. And if you're more familiar with p-adic cohomology, it's exactly the same, but not over QL, but over QP, QQ. There's an action of the p-power Frobenius, which is very important because as a vector space, you know its dimension, you know what it is, but the important thing is the action of the p-power Frobenius map on it, such that you have the following Lefschetz formula. Z is given by the product of these characteristic polynomials. So maybe I should explain a bit. So Fp was the action of the, so these HIX, they are functorial in X, where X is something in characteristic P. The HIX are vector spaces over, say, QP or QQ in my case. They have this action of the p-power Frobenius, so Fp to the a is the action of the q'd power Frobenius. So the determinant that's in there is something like a characteristic polynomial, and it's the reverse characteristic polynomial. And odd dimensional, so the odd degree cohomology is in the numerator, and the even dimensional cohomology is in the denominator. It runs from 0 to 2 times the dimension, but the dimension of x was n minus 1, so it goes up to 2 times n minus 1. Yeah, so computing a zeta function can be reduced to computing a Frobenius action on cohomology, up to sufficient p-adic precision. Okay. Now, since X is a smooth hypersurface, as Kieran already mentioned, we really only have to study the middle dimensional cohomology. By the Lefschetz hyperplane theorem, you can get rid of the rest. The rest is basically the cohomology of projective space in this case. Yeah, so we're only interested in Hn minus 1. So all these things are also explained in the paper for which Sebastian and I have written, and which I will give a reference to on the last slide. So if you're really interested in the details, you can look it up there. Okay, but now instead of taking a single X, I'm going to take a family. And a one parameter family. So I take some S in P1, the projective line, and over that I take a finite family, or I take a family of smooth projective hypersurfaces. So for every S in S, I got a fiber X of S. So how do you define such a family? Well, for example, with a polynomial, one of the fibers would be defined by a homogeneous polynomial in x0 up to xn of degree d, and the only thing I do is I add the coefficients are allowed to be polynomials of t, and they don't have to have any degree or be homogeneous at all. The t part is just any polynomial. So now every fiber has this rigid cohomology space, and what you need for the deformation method is that these glue together in a natural way, that one fiber has got something to do with the other. So the technical, the most theoretical way of saying is that together the Hn minus 1s of the fiber, this is true for any I, not just for n minus 1, but I only need it for n minus 1. They form an overconvergent F isocrystal. So I'm going to explain this and what this means in this case, but in general it means there's a connection matrix on it, so it's sort of like a vector bundle. There's a connection matrix on it, and a Frobenius structure, and a vector bundle, and the connection and the Frobenius commute. Yeah, so this map F is horizontal for the connection number. Anyway, I'm now going to explain this more concretely in this specific case. So you always start by lifting the defining equation of the variety of family to characteristic 0 in any way really, it doesn't really matter at this point. And we let phi, we still denote this by pi, be the family of hypersurfaces in characteristic 0. Yeah? So you come from one hypersurface to a family of hypersurfaces. And note that S doesn't have to be all of P1 because there might be some bad fibers. Maybe the hypersurface isn't smooth in some point, and those points we throw away because there you cannot guarantee that it's an F isocrystal. Okay, so what is this overconvergent F isocrystal? Well, basically in this case, it's just the algebraic de Rham cohomology, and it always is for if you choose the right lift. So you first took a lift of x over s to curly x over curly s. Now you take the de Rham cohomology. You have to take out the torsion because the torsion is not what you want it to be, so just tensor by QQ to get rid of the p torsion. And this thing carries a natural Gauss-Manin connection. That's known from differential geometry, basically just by differentiating cohomology classes with respect to t. That's basically what happens. Now you have to fix for the algorithm a basis of sections of this thing. So the Hn minus 1 were vector spaces of a certain dimension. Now I've got a vector bundle of the same dimension over my base S. And I let E1 up to EB be a basis of section, where B is for a Betti number. B is the n minus first Betti number of X. And we let M denote the matrix of Nabla with respect to this basis. So I haven't really explained how Nabla is defined because it was already mentioned before this week. For example, in the talk about like monomial deformations of Fermat hypersurfaces, it was mentioned that you can compute this with the Griffiths-Dwork method, and that this only really involves linear algebra. So this connection matrix M will have a denominator in general. So why does it have a denominator? Well, because there's bad fibers. There's fibers where the family is not smooth, so values of T for which the hypersurface is not smooth. And you expect to find those in the denominator of the Gauss-Manin connection. So the Gauss-Manin connection should be defined outside of these points. Over these points you still get a D module, but it's not locally free anymore, it's more complicated. Okay. So can be computed with the Griffiths-Dwork method, and we let R denote a denominator. So something which, if you multiply n by it, you get the matrix of polynomials. Okay, so now I was saying that an overconvergent F isocrystal is something which has both a connection and a Frobenius structure. So now I need to talk about the Frobenius structure. The connection sort of glues the fibers together, and Frobenius sort of commutes with the connection. That's what turns out to be true. But I wanted to give a bit more detail here. So here I've written down this ring of overconvergent functions on S, more or less. So S was P1 with the zeros of R, the singular fibers of my family, taken out. And there's a dagger on top of it. And if you've seen any rigid cohomology, you know there's always daggers. Yeah. So maybe this looks a bit technical, but so what does this mean? So there's a T to the I and an RT to the J. If you replace T by X and RT by Y, then these are just the functions that converge on a region strictly bigger than the open unit is in the XY plane. Yeah? And now the only thing I've done is add a relation. I've added the relation that Y is 1 over R of X or T. Yeah? So that's exactly what this means, and that's why it's called overconvergent. Why you need this condition is a bit technical, and this is not really the right place to explain that, but you can ask me about it if you want. And we let sigma be the standard p-power Frobenius lift on this ring, so there you can make a choice for the Frobenius lift. So what is Frobenius? Frobenius is the map that in characteristic T sends every element to its peak power. Yeah. But that still leaves lots of choices on this ring. So what do I mean by the standard one? Well, in QQ we only have one choice, because QQ over QP is unramified. And the p-power Frobenius is something in the Galois group of FQ over FP. So there's only one possibility because it's unramified. Yeah? But for T you still can pick lots of things. And we send T to the peak. That's what standard Frobenius lift means. You could also take another lift, but the formulas will be a bit more complicated. Okay, so now what we need about this Frobenius structure, that actually, so we had this family of hypersurfaces. Every fiber had a cohomology space, Hn minus 1 of x. Each of these cohomology spaces of these fibers had an action of Frobenius. And I want to glue this together. So the theorem now is that there exists a matrix in this ring of overconvergent functions, such that if you specialize, if you got a point T in characteristic P, you lift it to its Tuitman lift, and then you evaluate phi at this Tuitman lift, then you will get the Frobenius map Fp on this Hn minus 1. So this is quite technical, this follows from the theory. And so the important thing is that by once we've computed phi, we know all of the Frobeniuses of all the fibers. And we can stick those in this formula for the zeta function and compute all the zeta functions we want. Okay. Now it's also saying that on an overconvergent F isocrystal, the Frobenius structure sort of commutes with nabla. So F was horizontal with respect to nabla. So what does that mean in terms of matrices? So I define the matrix M of nabla, and if I define the matrix of the Frobenius, the p power Frobenius. Well, in terms of matrices, it means exactly this. That this differential equation is satisfied. So for simplicity, we're going to assume that R of 0 is not 0 mod P, and we let C be a fundamental matrix of solutions of nabla at 0. Yeah, so it's basically a fundamental system of horizontal sections. Okay, well, then you can show by substituting one of these into the other that the solution is given by the expression there. You have to conjugate by C, but there's a sigma somewhere because it's a semi-linear map. This means just that with respect to some basis it's phi of 0, but this you have to change back and forth to this basis in a semi-linear way. Okay, so this is very technical. Again, you can look it up in the paper if you're really interested. And the only problem is that to evaluate this at one of these diagonal lifts, you have to do something first, because these matrices C of T, they're given by power series expansions at T equals 0, and these power series expansions usually only converge for T smaller than 0, so the open p-adic disk. And the points where you want to evaluate them, these Tuitman lifts, they are on the border of this disk. Yeah? So this is not guaranteed to converge, and it will not in general. But you also know that phi is an element of this ring of overconvergent functions, so you just have to convert it to an element of this form, and then you can evaluate. So you have to multiply by a large enough power of R, and then you converge. I just wanted to mention this subtlety because it's lots of people get confused by this. When Sebastian wrote his first implementation of the algorithm, this was wrong, for example. He used to evaluate it straightforward. Okay, so now why is this interesting for algorithms? Because it seems like it's much more complicated, right, to study these families, but there's a real advantage. So what did Loder propose in 2004? Well, to pick a family with an easy fiber, more or less. If the Frobenius is easy to compute on one of the fibers, then maybe you can, by solving this differential equation, relate that to another fiber, a more complicated fiber, and well, reduce the problem from a hard fiber to a simpler fiber. Well, then for non-singular projective hypersurfaces, there is a particularly easy thing to deform to, and that's the diagonal hypersurface. So something which only contains monomials xi to the d. So I think it was called the Fermat hypersurface, maybe in the other talk. So why is it easier to compute the Frobenius or the zeta function for these? Well, because they have lots of automorphisms, and the cohomology decomposes according to these automorphisms, and you're left with, basically you have a one-dimensional problem. It's as if you were computing the zeta function of a curve, but a b of them, I guess. No, the dimension of the cohomology ones of them. Anyway, this is a lot simpler than it is for a generic hypersurface. Okay, so we can use this explicit formula of Dwork to compute phi of 0. It's not an explicit formula in the sense that it's easy to evaluate. It still takes significant time on a computer to evaluate it, but it's a lot simpler than what you can do for any hypersurface. Okay, so now we solve for this matrix C, and we have this differential equation which was satisfied here. Here are the horizontal sections, the solutions of nabla with respect to the chosen basis. We solve for that. We compute phi this way, because we already know, there's a mistake there, in the middle should be phi of 0. Phi is C, phi of 0, sigma C minus 1. And phi of 0 I know from the previous step, from this explicit formula of York. Okay, at the end we substitute the Tuitman lift of the phi that we're interested in, and then we know the Frobenius on the only interesting cohomology group, on the Hn minus 1. We stick that into the Lefschetz formula and we get the zeta function. Note that here I've been a bit sloppy because, of course, all these computations can only be carried out to finite p-adic precision. So you have to determine what finite p-adic precision, how many terms you have to compute to realize this p-adic precision. If you're solving a differential equation, you will introduce some denominators. You have to give estimates for how bad these denominators are. There's really lots of theory about this now. But this would be too technical to get into now. Basically, it's just this. This is the main idea. And maybe here I should say something about why I restrict to smooth projective hypersurfaces. It's because for smooth projective hypersurfaces you can always deform to a diagonal one. So it's not so clear what you would deform to for a toric hypersurface, for example, if you don't have the diagonal ones. But I heard this week from someone that there's this algorithm by Skurber and Voigt, which is very good at doing sparse, might be very good at doing very sparse families, or very sparse equations. So basically the only condition on x0 is that it should have the same Newton polygon or polytope of x, so you'd be able to pick one which just contains the vertices more or less, and I guess you would be able to do a lot better. If you're interested in doing things over large fields, for curves for example, then you can also deform to an x0 which is defined over a very small field. That can also be an advantage. Okay, so why would you do this? I think the main motivation for Alan Lauder was the time complexity, because he showed that the complexity of this algorithm is p-adic to the n to the O1 to a constant. So it's not the natural input size here is log p times a times d to the n. So for fixed p, what's in the brackets there is the input size. So for fixed p, this is polynomial time in the input size. Maybe I should say why this is the input size. It's because, well, log p times a is log of q. That's the size of the coefficients of the polynomial you need to define your hypersurface. D to the n is, for example, the dimension, more or less the dimension of Hn minus 1. It's also more or less the number of monomials, if I'm not mistaken, that you need to write down the defining equation. So my way of thinking is about this is that what's the genus for a curve is more or less d to the n for a smooth hypersurface. Somehow the geometric complexity of the object. Okay, so other algorithms which were available at the time all had a factor, at least a factor do to the n squared in the complexity, and I think both of them were also worse in terms of p, had a p to the n maybe in the complexity estimate. For AKR I'm sure, for Lauder 1 I think that's the case. The things that Kieran talked about a couple of days ago are better in p for sure, and might even be average polynomial time and all of this, but in the terms of the geometry they will still be d all of n squared, if I understood correctly. So by doing a deformation you can really do better in terms of the geometry. I should however mention that it's a bit ridiculous to focus so much on the complexity in d to the n, because this supposes that n goes to infinity, and even with this method we've only counted points on surfaces 3-folds, maybe a 4-fold here and there. So it's a bit ridiculous to let n go to infinity. From a practical point of view, this is irrelevant.
Yeah, but from the practical point of view, being able to get to n equals 3 is an advantage over the other method.
Yes, but maybe I'll say something about that. We cannot really do a lot for n equals 3 either. We can do some very sparse cases. Okay, so that's one thing, the time complexity reduced by Lauder for smooth projective hypersurfaces. Then Hubrecht did something similar for hyperelliptic curves. Those are not smooth projective, but almost they're smooth in a weighted projective space. And he showed that one could get the memory consumption down from 1 to 2. There's some remarks to be made about this. You have to do something special. You should not compute the c's, you just should compute phi straight away. there's a way of doing that, and then you can evaluate while you're computing phi, and then you don't have to remember so much. There's a way to save time there, but that only works if you take a hyperelliptic curve in a family over a small field, for example over the pi field. But that's not always a problem, because for example most elliptic curves, if they have the right contortion, they're contained in the Legendre family, so you can take them as a big fiber in a small family. So lambda in an enormous field, but the Legendre family is defined over that. So there's also some particular applications for which this is supposed to be good. For example, like big fibers and small families, they have a family defined over Fp, and now all the way at the end you're going to take a fiber in Fp to the 100. Then most of the computation can be done over Qp, all the way up, so like solving the differential equation, computing the matrix product, all of that is over Qp. Only in the very last step, when you put in the Tuitman lift, you have to do something over a bigger field. So this is a way of doing much bigger things, but they're also less generic in a way, because I'm just saying that more or less every elliptic curve is defined is contained in a family over a prime field, but that's not true in general. You get something like that. Get a restriction. If you wanted to use this in cryptography, then you might be afraid that there's special attacks for curves contained in it. And if you want to do lots of fibers in the same family, but again, because again, once you've computed phi, you can basically do all of the fibers just by substituting and putting into the Lefschetz formula, which usually only a small percentage of the time. Of course, in some limits, when you go to enormous fields, this step does become normal and important. Okay, so our work, the work of Sebastian and me, we showed that the time complexity was a bit better than Lauder thought, than is mentioned in Lauder's paper. There's a complicated expression, so I've let omega denote the least exponent for matrix multiplication, which should be somewhere in the interval indicated there. But so what should you remember about this? That this is an improvement by a factor pt to the n. So Lauder had O of p squared, and we have O of p, and we get rid of one of the d to the n's, which is maybe not that spectacular. But the O of p is sort of important, and it also, I can maybe explain where it comes from. Lauder, to compute phi of 0, he uses these formulas of Dwork, but these formulas of Dwork, they're naturally defined not over Qp, say, but over Qp of pi, where pi is a Dwork pi. So that means that pi to the p minus 1 equals p or minus p. Yeah. So if you compute in this field, then the extension degree of this field has a p in it. Yeah. So every single multiplication will already be O of p, and you still need O of p of those. Yeah. But the result you end up with, this Frobenius matrix at the end, will still be contained in Qp, or in Qq, in the unramified field. You don't really need the pi's, they cancel out at the end. So what we did is we showed that they cancel out and that you don't have to compute over this bigger field. So that gets rid of one of the p's. And then the d to the n is a bit complicated. There have been lots of improvements in since Lauder's paper about how you can compute Tuitman lifts or Frobenius substitutions, these sigmas, by using like fast modular composition and things like this. So I think the d to the n should come somewhere there, but I haven't really looked in at enough detail at Alan's paper to be exactly sure where the d to the n comes from. Okay, so that's one reason why it might be interesting to read our paper, because the complexity is a bit better. What is another reason? Well, because we collect all of the known tricks. So some of the things that Kieran talked about, for example, these Newton-Girard identities and the Hodge structures. So both of these tricks have been mentioned in the papers, but I think not in the same paper at once, and you can really combine them, because both of them, well, if you put them together, you get something more efficient than if you do them separately.
I thought they were both in my paper on cyclic cubic defaults.
Maybe they are. Yeah. But I think in that case, maybe there's no general theorem that says what the n precision, what you can take the n precision to be, right?
Yeah, I didn't
Yeah,
phrase it
but definitely all the ideas are in Kieran's paper on cyclic cubic threefold. This idea of using Hodge structures is joined from Kieran and Alan, I think, and then the Newton-Girard identities are from Kieran. So we just combine all of these tricks. We do the best thing known for all of these things. We take the best convergent bounds for Frobenius structures on connections. I define this ring of overconvergent functions, and you can see that if you cut off modulo some precision p to the n, that you will get a rational function. So that rational function will have a pole of some order, and now the question is, what is the order of the pole? And there's sharp bounds by Kieran and joined between Kieran and me. that we use in the optimal way. And then there's, I said there are denominators if you solve this C, this matrix of local solutions, and we also use the best thing available in that case. To get all of the precision bounds as low as possible. Also we don't restrict to p bigger than n, so we also give bounds for denominators that might appear in Frobenius. It's all as sharp as I know how to do, and I think it's the sharpest known in all cases. Okay, and then maybe most importantly, there is a highly optimized implementation by Sebastian and Flint. This implementation is restricted a bit because it starts with a family over Q. When Sebastian started working on this, he didn't have p-adic code to work with because he programmed everything from scratch. So he defined his families over Q, and he wrote this enormous and very efficient code to compute Frobenius matrices. So we're a bit stuck with that. There's no real reason to restrict to that. It's just that that's the way the code has been written, and it might be more efficient as well. And there might be applications to like average polynomial time things, but it's all very speculative.
Before you go, is E the base of the natural
Yeah,
logarithm?
E is the base of the natural logarithm.
How does that
So somewhere in the dimension, let's see, so if you take all monomials of degree d in n variables that satisfy a given condition, and you take a limit there, then you get an E somewhere. That's where the E comes from.
Is it because the n factorial? It's
Yes.
like the number of
N to the n
points.
over n factorial.
Number
N
of
to
points
the n
and d
over
times
n
the n times the
factorial.
simplex. D
Yeah.
times the simplex is.
This comes up in this comes up in the non-general too.
Yes. Yeah, so it's something to do with binomial coefficients. Yeah, so for now nothing has been done in Sage. So what would be needed to do all of this in Sage? Well, first of all, computing this connection, it's easy if you take a family, a sparse family that contains few monomials. So we always take diagonal monomials in our family because we want the fiber at 0 to be diagonal. But then the monomials of the diagonal, if you just take 1 or 2, you'll get something very efficient. It's very easy to compute the connection matrix. These are the things that have been done by for example, Gauss-Manin and by lots of people. They're computing the connection matrix is really not an issue there. But if you take a dense family, so you take all of the monomials in your equation that you're allowed to take, then you got something which is very bad, and in fact no one was able to compute the Frobenius matrix in these cases so far. So Lauder used the Gröbner basis code for this, which you can draw out of the window for such big problems, but even using sort of naive linear algebra is not enough to do it. If you do like Gauss elimination or something, you won't be able to do it because you get enormous degrees and enormous coefficients. You have to use that these matrices are sparse, which might sound a bit strange. So even if you take a dense polynomial, a polynomial that contains all of its possible terms, then the matrices that you have to solve, or they have to invert, or they have to, well, you shouldn't invert any matrix, but when you're solving a linear system, these matrices are still sparse. They'll always be sparse. And so you need to take advantage of that. So you need to use these techniques from numerical linear algebra, or it's not really numerical, but like large linear algebra, LUP decomposition. So L means lower diagonal, U means upper diagonal, and P means permutation matrix. So the matrices that come up in our computations, you can factor it like that, and once you have done the factorization, you can solve the system LUP equal to something for many somethings. Yeah? And that's for these reductions. You have to reduce lots of things in the cohomology, so you do this LUP decomposition once, and then you can reduce lots of things. That's very important. And a lot of work to implement. And I guess it's not in Sage, although I'm not very familiar with limbox and these things, I don't think it's in Sage. Okay, so for the case when tau is not contained in the prime field, if you take a bigger fiber, then we need a better implementation of QQ, because at the moment Tuitman ellipse and Frobenius substitution are all horrible basically. They've been implemented in quite a naive way. So this is all contained in Sebastian's code. So Sebastian has connection code, deformation code, p-adic code. This code will soon go into Flint 2.4, I think. I'm not exactly sure whether this has already happened or is sure to happen. And that should then at some point go into Sage. So that sort of, I'm not very motivated to implement these things in Sage because I think that they will end up in Sage automatically. It just might take a couple of years. And Sebastian's code is very efficient. He's a really good programmer. So me, for example, I'm sure I cannot do better than he can. And he's too busy, he works at the bank now, so. Okay, so the paper about this, with all the combination of all the best tricks and all the best bounds, you can find on archive at that link, and the code you can find on Sebastian's GitHub account. So it's in the repository, which is called Deformation. He's got lots of different repositories, but there you can also take a look at his p-adic, his q-adic code. Yeah. Okay, so now I have to see how much time I have left. If I have any time left, maybe a tiny little bit, right? Like 5 more minutes, is that okay?
Sure.
I wanted to show some examples. So, terminal. Should go, okay, that is right. Okay, now I need to do information master. So this is the thing I've downloaded from Sebastian's repository. So it's in examples. So let's do a quick example to explain how the input and what the input and the output look like. So I've already compiled this, just to be sure everything's alright. So what's the family of hypersurface here? Well, in this case it's a curve, so it's something in P3. So there are 3 coordinates, x0 up to x2. And this pair of brackets here, that means x0 to the power 5. And this is x1 to the power 5. And this is x2 to the power 5. So these are the diagonal terms. And then off the diagonal we have a term x0 to the 1, x1 to the 1, x2 to the 3, which is also of degree 5 obviously. And there should be a polynomial in t in front of it, the coefficient. And what is this polynomial of t? Well, it's just t in this case. So it says that it's got 2 terms, and the constant term is 0 and the linear term is 1. This is Flint, standard Flint input actually. Okay, so then the Gauss-Manin connection is computed, and that takes basically no time. Its denominator is there, r. So it's only of degree 5, which means that we'll be able to do very fast computation. And now we've computed something over an extension field. I'm not sure which one actually. So I can take a look here. So I go, let's see, this is not mentioned in the output I think, it's no problem. So, up. So D is 40, it says here. So this is actually the zeta function of this family at a fiber defined over, at a fiber contained in F3 to the 40. And the tau is contained in F3 to the 40. So this is quite a nice. Yeah? But on the other hand, the geometry is very simple. This is just a family of, let's see, the B5 curves. I'm not sure what that actually is. So now maybe a little bit more interesting example. So we go example 0, 2, let's see. No, let's see. Again, very fast. So what has happened here? Here we've taken a quartic surface in P3, so a K3 surface. The diagonal terms are here, x0 to the 4, x1 to the 4, x2 to the 4, and here at the end x3 to the 4. There's one term of the diagonal, which in this case is t times the product of all variables, so x0 times x1 times x2 times x3. Yeah? So this might have been the exact same example that from the other talk, but I'm not sure, maybe it's not exactly the same. Anyway, the denominator of the connection is t to the 4, and we've computed over p to the 40, so 3 to the 40, so we're really able to compute the zeta function, not just the number of points, but the zeta function over f3 to the 40. Okay. And now because someone asked me about it, I wanted to show a couple of examples for bigger p.
Jan?
Yeah.
What is this T1?
That's the tau, the variable. So the fiber at which I evaluate. Yeah?
Why? Okay.
So
x is the root of a degree 40 polynomial.
yes, which would suggest that the degree is maybe smaller here, right? But I think this is because we've taken something from another paper. We wanted to compare against exactly the same example, and that's why we took this one. I can look it up. It might be that it's degree 19 or 20 extension. But anyway, you can do things over enormous fields if you stick to families that are this easy. You can even do a lot bigger P. So let's see what I did here. I just did this afternoon, so I haven't checked that the output is correct, for example. So 2P is 2009. Maybe I'll let this run. This should. So the same idea, but now we. Forward slash. Sorry. A bit of a noob with computers, so I'm really very proud that I'm able to use this code. So it's the same family, but now T1 is just 1. Yeah, I've taken a much bigger P, and I take the fiber at 1. I'm interested in the zeta function of the fiber at 1. So just the zeta function of all variables to the power 4 plus T times all variables to the power 1. And this should take, I don't know, like 20 seconds maybe I'll let it run. So I think we can do quite big fields. I also tried 10,000, this is already 10,000, sorry, I tried the biggest one maybe. I accidentally took P is 10,007 here, and now it should take like 3 minutes, so maybe I'll just let it run. So, but the thing is that we really can do P is next prime 10,000. But this is, because in this case this connection has very, this family is very sparse. So the degree of the connection matrix is very low. For generic, we've also done generic cases, then you'll get, for R you get a polynomial of degree 200, for example, which will make things like 50 times as slow at least. Yeah. But I haven't tried the example that Kieran showed on the slide. I would really like to do it to see how well it compares. The only thing I'm afraid of that since we're computing the connection matrix over Q, we might run out of memory. Okay, so I want to leave it at it. Sorry for going a bit over time. Thanks for your time. Yeah, so in total this is maybe, now I'm not sure if it was 1,000 or 10,000 again, because I ran this before for 10,000 and then it took like 300 or 400 seconds, and now it's only taken, yeah, so I'm not sure. Yeah, but this is either P is next prime 1,000 or next prime 10,000, and you can do both of them within a short amount of time. Yeah.
Are there any questions for Jan? No, let's thank him again.